Okay, we're looking at a little maths activity here, practical activity, and it says your job is to create a tray which maximizes the volume. Follow the steps below. Okay, well, you should have sticky tape, ruler, scissors, piece of square paper. You're in pairs. Diagrams below, I'll show you, you can't quite see them yet, but I'll show you on a camera. Person A will assemble one model, person B will assemble another. So person A will assemble a model. Your number is 3 centimeters, your measurement is 3 centimeters. Person B, your measurement is 7 centimeters. Just remember that for in just a moment's time. So you have your sheet of paper, make an open square tray by first accurately measuring identical squares in each corner. Then cut them out, rule dotted lines, I'll show you in a minute, then fold up the sides to form trays. And you can use sticky tape to secure the sides. Alright, so person A will do model A. You'll have 4 identical squares removed, and each of those squares has a side length of 3 centimeters. Model B, or person B, will do the same with 7, and then you'll compare them. You and your partner will notice that removing smaller squares gives a shallow tray with a large base, and removing larger squares, that's person B, gives a deep tray with a small base. Notice that we're going to use X to show that the little squares we take from the corners can change. Okay, and that will also, the little X's will be the height and depth of the tray. Let's have a look. Okay, so the first step is for person A to get your piece of paper. Person B, also you'll get your piece of paper, and the measurements I'll say in that order, person A then person B. Start by measuring squares in each corner. So we've got 3 centimeters we need to go in for person A. 1, 2, 3. Mark that in. And across 3 centimeters. 1, 2, 3. Try and be accurate, try and be precise. We have one of the squares, we do the same for the other sides. Okay, so just to speed things up, I've now edited that bit, and you see that we've got our 3 centimeter squares. Okay, all in the corner there. Person B will do the same with the 7 centimeter squares. As you can see, they look very different. We've got extremely big squares and much smaller squares. Pieces of paper are the same size. So let's see what happens when we cut them out. Okay, as you can see, we've cut out the smaller squares there. Alright, there's 4 of them, and we have the shape of the smaller squares. Now for the bigger one, and believe it or not, this is what's left over. So it's an extreme case, and in fact I'm using slightly smaller paper than you will in the Prac. Yours will be 21 centimeters by 21 centimeters, and mine's closer to 16 by 16. However, the differences between these two shapes are very noticeable, aren't they? Yet they both came from the same size paper. All we did was vary the side length of the square in each corner, and then cut them out. The next stage is to rule up some dotted lines and fold it up. So let's have a look. So with our piece of paper with the 3 centimeter lines drawn and the squares of 3 by 3, we draw some dotted lines along here. Along here. And we'll complete our way around the whole shape. These lines are important, they will guide our folding of the paper. Notice how we have X along here, which is 3 centimeters in this case, X along here, 3 also. But also notice how this 3, or this X, is the same as the side height of the box. You can say the same about this one too. So if we fold them up, this is reused paper. You can see somebody's old quiz on the back. How many did they get right? So as you can see, when we fold them up, they're going to form this open box or tray. And when we're finished, we've got a full box, and it's time to get the sticky tape on it. So I've used my sticky tape, and you can see we have a box or an open tray. Okay, so that was a flat bit of paper, but now, alright, we have a box or an open tray. Let's do the same with the other one, with the 7 centimeter square sides. Well, here it is. It's an extreme box. Okay, it's very long. I had a little bit of trouble taping it up. Hopefully yours will be better than this because your piece of paper is a bit bigger, but it is very, very different shape. Let's compare the two. Box number 1, where X, the little square sides that we removed, is basically has a big base, large area, cross-sectional area there. It's fairly shallow. Whereas the other one, which you'd be flat out calling that a box, but it has got a base, it's down the bottom, it's a very small shape, very small square shape. Cross-sectional area is small. The depth is very deep. So if you compare the two, okay, so the little thin box, I won't call it little, but it's very deep with a small area. It has a great depth. So while it doesn't have much area in the bottom, it has a lot of depth. This one has little depth by comparison. However, it has a lot of base. It has a lot of cross-sectional area. Part of the experiment, you'll be using your volume of a rectangular prism formula to find what the volume of each of these are and which one has a bigger volume. As X changes, as the size of the square changes, that is removed from each corner, we get from a bigger, shallower box to a much deeper but thinner box with a small cross section, a small square base. And as we increase X, that gradually, this shape gradually becomes that shape. Alright, so it happens gradually because we can change X to anything we like until we run out of base. So let's do the prac, and then there'll be discussion after that.